bit finish up here on chapter 4, which was sort of finishing up bonding. But really what we talked about, I think last time for the majority of the time was geometry. And when we do geometry, there's really kind of two things to look at. One is if you're ever just dealing with diatomic molecules, as we talked about, which are basically guys that just contain two atoms. The geometry, again, is always going to be linear. Because there's only two, they can only be arranged basically in a straight line of each other. And as we talked about, it doesn't matter if it's two of the same elements. It doesn't matter if it's two different elements. It doesn't matter if there's a single bond, double bond, or triple bond. If you're doing the geometry of something that is just two, it's always going to be linear. When you get into three or more atoms, that's really, again, where you need to always look at the central atom. And really, there's two main things that are important when you're doing it. And one is basically how many electron pairs there are around that central atom. And remember that when you're counting electron pairs for geometry, it doesn't matter if they're dots, which are non-bonding electrons, doesn't matter if they're lines, which are bonding electrons. And it really doesn't matter if they are double bonded or triple bonded. They all count basically as one electron pair. When you determine how many electron pairs there are around the central atom, that will give you the one type of geometry name that we talked about, which is sometimes referred to as the electron pair geometry name. So for example, if there are 3 electron pairs, the electron pair geometry name is trigonal planar. Now, there's a second name that's commonly used as well, which is what is referred to as the molecular geometry name, or really the shape of it. And depending on really the type of electron pairs there are around that central atom, as to sort of the overall shape that will occur. When you have just bonding atoms, or sorry, bonding electrons, which are lines, what you end up getting is really the electron pairs, they're all attached to atoms, which means the electron pair geometry name and the molecular geometry name will be exactly the same. Because as those electrons move, they're actually moving the bonds with the atoms, and everybody ends up in the exact same sort of geometry that we see. It's only when we introduce non-bonding electrons or dots around the central atom that we actually get rid of a bond in an atom, and it also gives a little bit more room for everybody really to spread out. And the idea behind it is that electrons are negatively charged, so when they are near each other, they really don't want to be near each other, but they can't escape because they got to keep within a bond. So as we introduce non-bonding electrons, we start to see a difference in the molecular geometry name. In an instance like these last couple here, we have those non-bonding electrons that occur, and we do get some differences in the name. So for example, something like water that we saw, which has 1, 2, 3, 4 electron pairs. And because it has 4 electron pairs, the electron pair geometry is going to be tetrahedral. But because of those non-bonding electrons, and it really only has 2 bonds in this case, those non-bonding electrons are really going to try to go as far away as possible. So as those electrons kind of go up, the bonded atoms also try to get away as far as possible. And what ends up happening, because we no longer have actual bonds here and atoms, and we have just those electron pairs in that sort of empty space, if you will, they're really able to sort of spread out a lot more. And we end up with a molecular geometry, as we talked about, of something that's referred to as bent or V-shaped. Hence why water is always sort of drawn like that, like a V upside down. And again, it's really when you draw your Lewis structure, if you see those dots, that's when you're going to have a difference in both of those names. If you draw your Lewis structure, you really don't see dots on the central atom. Both of those names should always be the same. Any questions on that stuff that we talked about? And I think we made like a table last time, maybe, as well as we went through it. So the last thing we're going to talk about is molecular polarity. And when we talk about molecular polarity, we're talking about the overall molecule as a whole. So earlier on in this chapter, we talked about what's commonly referred to as bond polarity. And bond polarity is just simply using the difference in electronegativity values between 2 atoms within a bond and to decide, are they going to share those electrons equally? Or are they going to share them unequally? When we talk about molecular polarity, we're really talking about the entire molecule as a whole, every bond that is present and what is going on with it. We oftentimes will sometimes use similar symbols for polar molecules. If you remember, sort of in bond polarity, we draw this sort of dipole arrow where it points to the more negative side. And again, this side, it kind of makes like a positive sign to the more positive sign within a bond. We also use a similar arrow for a polar molecule. And when we talk about the molecule being polar and we draw this arrow, this is what is sometimes referred to as the dipole moment. And it really means the same thing. It points to the spot in the molecule that pretty much all the electrons are hanging out. It's a little bit more negative. And it points the other end to the side that obviously is a little bit more positive, where the electrons are sort of unequally being distributed. So there's really kind of two classes of molecules that we look at when we think about molecular polarity. And let's start with really sort of the easier one of all of them there, which would be when we're dealing with diatomic molecules. So when we're talking about diatomic molecules, which obviously only contain two atoms, if we have something like F2, like we've seen before, when we look at this particular molecule, it pretty much has just one bond, and it's obviously the bond between the two fluorines in this case. Based on electronegativity values here, we know that this guy's 4, this guy's 4, which means if we do that change in electronegativity, it gives us 0, which means we do know that this bond is a non-polar bond, which ultimately means that it's sharing electrons equally between both sides. Now, in this particular case, this bond right here, which is the one we're talking about, is the only bond in this entire molecule, which means because it's the only bond in the entire molecule, and that molecule happens, or that bond happens to be non-polar, we would also expect that this molecule would be a non-polar molecule. Now, if we looked at something like HF, which is also diatomic, looks something like this. The difference between hydrogen and fluorine being the most electronegative, we would draw the bond dipole arrow heading in this direction. And we would know that that bond is going to be a polar bond in this case, the one between the hydrogen and the fluorine. Again, fluorine about 4, hydrogen about 2.1. So that's like a 1.9 difference between them when we do our difference in electronegativity. Now, for the exact same reasons we see on the left, this bond right here, which we know is a polar bond, is again the only bond we got going on in the entire molecule. So we know that this guy is going to be a polar molecule, where this is our dipole moment arrow heading towards the fluorine. That again means that the fluorine side has more electrons hanging out over there, and the hydrogen side has less electrons hanging out over there. So the one place where bond polarity equals the molecular polarity is with diatomic molecules. So it's really the only place where, if you're able to determine that bond is polar or non-polar, it's going to be really the same answer for, is the molecule going to be polar or non-polar? And that is, again, because there's frankly just one bond. So whatever that bond is what that molecule is going to be. If something is non-polar, it means the same thing as what we talked about with a non-polar bond. It means we expect overall equal sharing of electrons, which means overall, something like F2, there really is not a side that's more negative. There's not a side that's more positive, sort of neutral, if you want to kind of think about it that way. There's no real positive or negative charge, as opposed to what we see in HF, the, again, fluorine side more negative, hydrogen side more positive. Question on diatomic molecules. So again, that's really the only place where you can do bond polarity and molecular polarity, and they're pretty much going to be identical to each other. Now, it does get a little bit more difficult when we're not dealing with diatomic molecules. So when we were dealing with 3 or more atoms, you basically have to look at 2 things. You have to look at, first off, are there polar bonds? So you have to look at the bond polarity in this molecule and see, are there polar bonds? Clearly, if the answer is no, there's no polar bonds, then that's your answer for whether or not it's polar or non-polar molecule. It would be a non-polar molecule. The second really important thing that you have to look at is the molecular geometry. So not the electron pair geometry, but the molecular geometry, which is sometimes referred to as the shape. So 3 or more atoms involved, you got to really look at those 2 things and see, are there polar bonds and what is the shape of it? So a common example, if we draw something like our friend here, carbon dioxide. When we look at the bond between carbon and oxygen, is it a polar or non-polar bond? It is a polar bond. And again, this is one where carbon and oxygen, again, are in the exact same row, and oxygen being more electronegative. So we can draw our sort of dipole arrows heading towards the oxygen. So this thing is, yes, it does contain polar bonds. So we do have to look at the second thing here, which is what is the geometry? And when we look at the central atom, it has 2 electron pairs and it has 2 bonds. So something with 2 electron pairs and 2 bonds has a molecular geometry of linear, which basically means it's a straight line. So what we end up having in this case is something that's like a straight line. And we have an oxygen on one end pulling this way. We have an oxygen on the other end pulling the other way. And I'm actually pulling on my pen, and I can see my pen is going really nowhere in this case. So what ends up happening in this case, although this thing does contain polar bonds, because of the geometry, they actually do cancel each other out. And this would actually be a non-polar molecule. The reason they cancel each other out is these guys here that we draw, which are these bond dipole arrows. They're what they call, I think, in physics, vectors, which have direction, they have magnitude. Then I fell asleep. Then I woke up long enough in physics to remember in certain cases, they will add to each other. And in other cases, they will cancel each other out. And in this particular case, basically, we got 2 vectors heading in equal and opposite directions. Very commonly, people think about like pulling on a rope. So 2 people pulling on a rope, equal and opposite, like tug of war. The little flag's not going to go anywhere and they cancel each other out. So CO2 is a really good example to indicate that you definitely can have a molecule that has polar bonds, but because of the geometry, they may actually not be, it may be a non-polar molecule because they do cancel out. If we look at something like our water that we also saw earlier, again, between hydrogen and oxygen, the oxygen is more electronegative. So here our bond dipoles would be drawn in this way. So it does have polar bonds. The geometry here is 4 electron pairs, as we talked about, I think, on the last slide, and 2 bonds. And that would give us our bent, our V-shaped. Now, in this particular case, what we have is basically something that's kind of like a V, and everybody's heading towards the top. So you can almost imagine like pulling a string from the top. The whole thing is going to sort of rise and move. And in this case, they actually will add to each other. And what we get is what is referred to as a net dipole moment happening in this direction, where again, the oxygen side is more negative, the hydrogen side of water is more positive, and this is what is referred to as the net dipole moment. And in this case, if you ever did a little vector addition, you basically got this guy going this way, do a little head to tail action like that. And in this case, they basically join heading in that direction. And that is where we actually see it occur. So because of the geometry here, we actually do get a polar molecule that occurs. But who wants to deal with vectors or things like that? Nobody really does. So there are certain geometries when you're looking at it, which are sometimes referred to as symmetrical geometries. And basically some symmetrical geometries. For your cases, we did trigonal planar. And these are molecular geometries we're talking about here. So these are the molecular geometries. We have tetrahedral. I think for you guys, that is it. So what these guys have in common is, if you remember, if you draw the Lewis structure for these guys, there pretty much are no dots on the central atom. So there's no non-bonding electrons on that central atom. And if you have one of these two geometries and all the outside atoms are the same element, they will basically be symmetrical to each other and pull equal or push equal to each other, and you will end up with a nonpolar molecule. So for example, if we draw something like CF4 here, we'll draw all of the dots there in the back on the outside here. But when we look at the central atom, which is always important here, what we would look at is there are no dots on the central atom. Every element on the outside is the same. This guy has polar bonds heading towards the fluorine. And this means that we will get them all to cancel out. And this would be a nonpolar molecule in this case. Now, what happens if I take the same situation and swap out one of the fluorines for a hydrogen? In this case here, we have the carbons heading towards the fluorine, but in this case, we now have a hydrogen, and a carbon-hydrogen bond is nonpolar. So what we end up having in this case is actually like three of these guys kind of pulling to the left, and the guy with the hydrogen really not pulling back the other way. He's actually going with them a little bit. And what you could kind of visualize is we're going to get kind of a net movement that's going to happen. So if you happen to have one of these geometries where you have no dots on the central atom and everything on the outside is not the same element, it will actually go from a nonpolar molecule to a polar molecule in that case. So these symmetrical geometries of trigonal planar or tetrahedral, no dots on the central atom, everybody on the outside is the same element. It is almost a safe bet just to write nonpolar molecule. These geometries here, no dots on the central atom, everybody on the outside are different elements, or at least one different element, probably a safe bet to write polar molecule in that particular case. That leaves us some unsymmetrical geometries, which for our cases here is our angular, it's our trigonal pyramid, and it is our bent, our V-shaped. And what all these guys have in common is basically when you draw your Lewis structure, there's dots on the central atom. So in this case, you draw it, you got some dots. And if this is the case, you draw it, you got some dots, and all the outside atoms are the same, it is most likely going to be a polar molecule. So like our water that we just saw there a second ago, I see dots on the central atom. I see everybody on the outside is the same. I see it's a polar molecule. And again, in most cases, you will be probably correct, and probably 99% of the time. So these are really quick ways that you can, based on just looking at your Lewis structure that you draw, make a fairly good determination of whether or not your molecule will be polar or nonpolar. And again, we're talking about molecular polarity, the entire molecule as a whole. That really leaves only one left for three or more, which is linear. And linear is a pretty easy one to figure out. If you got two things like we did with CO2 going opposite of each other, it's going to be nonpolar. If you have two things that are the polarities heading towards each other, it's also going to cancel out. It's like two people pushing on opposite sides of the door. It doesn't go open or shut. But you could have a linear situation where everybody is heading in the same direction. And in that case, it would be a polar molecule. So linear, which is a straight line, is pretty an easier one to sort of figure out. This is a very good way to very quickly just look at a Lewis structure and, like I said, make a pretty educated guess as to whether or not it is a polar or non-polar molecule. Question, yeah. So did you say polar molecules? Is that what you're saying? Non-polar, yeah. So non-polar molecules, yeah, pretty much you have all the same ones on the outside. And the other important part of that is there's like really no non-bonding electrons on that central atom, so no dots. And that's definitely going to be in pretty much all cases a non-polar situation, because they will basically be equal and opposite of each other outside of linear, obviously, but they'll be equal and opposite of each other in that case. Again, when we get into sort of our guys with the dots, what we end up getting is we have usually some unsymmetrical geometries, and that's really a result of those dots actually being there as non-bonding electrons. So we also have those non-bonding electrons, which in reality have a little bit of a pull as well because they're non-bonding electrons, and that usually will lead to a more polar sort of molecule. Other questions on that? So if we just quickly kind of look at these, kind of doing what we did before, we could look at this here, and we do not see dots, right? So it tells us it's symmetrical, but when I look on the outside, right, they are all not the same element, which tells me it's going to be a polar molecule in this case. And it's actually the carbon and oxygen part that is polar. When I look at this guy, I have no dots on the central atom. Everybody on the outside is exactly the same. The overall molecule here is going to be non-polar. I look at this guy, I see dots. I see everybody on the outside is the same. So dots tell me most likely going to be polar molecule. And here I see no dots, but everybody on the outside is not the same. So it's going to tell us that it's going to be a polar molecule. So that is almost as quick as you could actually do it by just looking at those simple things like that. And like I said, maybe not 100%, but pretty darn close. You're going to be probably correct if the question is, is it a polar or non-polar molecule? So if we just kind of back up and maybe look at a couple that we did, I think the other day, bless you. Actually, here we'll go back more. That's where we're drawing, I think. Bunch of them, maybe. There we go. So for example, we could go through this one here and kind of do kind of the same thing. Again, would we expect this guy to be polar or non-polar? This molecule. So again, I look at the central atom here, the guy at the top. I look at the central atom, I see dots, right? And I see everybody's the same on the outside. That's going to be a polar molecule. I look at this guy, polar or non-polar based on geometry. It's going to be non-polar, no dots. Everybody on the outside is the same. It's going to be non-polar. This guy here, polar or non-polar? This one at the bottom. That is going to be non-polar. This is actually a diatomic molecule, which means it has just one bond, and the bond is two nitrogens together, which means that's going to be a non-polar bond, and it's also going to be a non-polar molecule. Polar or non-polar for this molecule? Based on geometry is going to be non-polar. There's no dots, and everybody on the outside is exactly the same. So that's that tetrahedral geometry, which is a symmetrical geometry. What about over here? What is the geometry of this guy? The geometry of this guy is? Its geometry is linear, so we do need to actually look and see what's going on. Carbon, hydrogen, polar or non-polar, that bond? Carbon, hydrogen bond is actually a non-polar bond. It's that 0.4 difference. Carbon, nitrogen, which is the same row on the periodic table, is going to be a polar bond. So it's actually going this way, right? Not much going on between the carbon and the hydrogen, which means because it's linear in this situation, you got one guy just pulling that way, right? Which means you could imagine it moving, and it would actually be a polar molecule in this case. Yeah, so again, that's kind of two different things in a sense. What you're talking about is the electronegativity chart, I think. And what that ultimately tells you when you do the difference in that is whether or not the bond between those two elements are going to be polar and nonpolar. And the one place when we talk about molecular polarity where that is exactly the same is a situation like this guy down here, where there is only basically one bond in that molecule. And because like that one bond, if you did the electronegativity difference, would be a nonpolar bond, and that's the only bond in the entire thing, then that those two will match up always. So that would be a nonpolar molecule that has a nonpolar bond. But when you do get into something, say like the guy up here, where you have 3 or more atoms, you have to look at 2 things. You have to look at whether or not there are polar bonds, which in this case there are. They're actually heading towards the sulfur in this case, sulfur being more electronegative. And you have to look at the geometry in this case. So when we typically look at electronegativity differences, is usually for what is referred to as bond polarity. When we think about the entire molecule as a whole, it's sometimes referred to as molecular polarity. And in certain cases, especially with 3 or more atoms, they are different things. But if you're only dealing with 2 atoms, then they will basically be the same. Other questions? Questions on geometry or any of that stuff there? Okay, that does wrap up this chapter, I believe. So we will roll into the next chapter here, to chapter 5 here, which is chemical reactions. So we're going to talk about balancing equations. We're also going to talk about different types of equations, I think, in this chapter. We'll also talk, I think, about grams, moles, and some stoichiometry type of calculations. So let's start with actually equations. So when we have an equation really does represent a lot of times a chemical reaction is taking place or a chemical change that takes place. And 100% of the time, pretty much in chemistry, if you have an equation, as we'll talk about here, we want to always make sure that it is balanced. In most things that you do, if you need to use the equation, it needs to be balanced. And there's really a few different parts to the equation. First off, on the left-hand side of the arrow, that is what we refer to as the reactants. So the reactants are left-hand side of the arrow. They are the starting materials in a chemical reaction. They're basically what you toss together to get the reaction kicking off. On the right-hand side of the arrow, that is what is known as products. So the products are obviously the substances that are produced as a result of a chemical reaction. All chemical reactions, basic chemical reactions, really involve electrons and bonds. And basically what's happening is we take all the bonds on our reactant side, our starting material, everybody kind of breaks apart, and then they basically reassemble into new substances on the product side, make new bonds as a result of that. And that's really why chemical reaction oftentimes is obviously a chemical change that occurs. As we talked about in a chemical change, what we start with and what we end up with is fundamentally 2 different things. Although we do sometimes use chemical equations to represent physical changes. For example, we can see an equation sometimes, like if we take water in the liquid phase to like water in the solid phase. This is really a physical process of freezing, right? We take liquid water to solid water, which is ice. So we sometimes will use an equation to represent some type of physical change. Now, there's other things that we commonly see in equations. Very commonly, we will see sort of symbols next to formulas, and the symbols typically represent the states. So S is solid, if we see it. L is liquid. G is gas. We also very commonly will see AQ, which is aqueous. Aqueous is really a water environment. And sometimes people have a question about, what is sort of the difference between an L and an AQ? So typically an AQ is oftentimes referred to as a solution. And a solution is really a homogeneous mixture of really 2 or more things together. So for example, if you had just water by itself, nothing else there, that is basically a pure liquid. If you take water, which is a pure liquid, and you add some sodium chloride to it, which is salt, the salt will typically dissolve in the water. And what you are left with is a sodium chloride solution, which would get the aqueous symbol. So something that is aqueous is typically made by taking something and dissolving it in something else like water. Water is sometimes referred to as a solvent. And that is, again, the difference between that and something that gets the L symbol. The L symbol is just a pure substance by itself. Other common things that we see in equations oftentimes happen on the arrow. We will sometimes see a little delta symbol, which usually will mean heat. You may see things written on there, maybe like metals, like a platinum. Yeah, you may see something like H plus, which is an acid. And these are sometimes, a lot of times, where we will put things that are referred to as catalyst. And catalysts are things that are added to a reaction, in most cases to speed up the chemical reaction is typically why you add a catalyst. So usually added to speed up a chemical reaction. But it is important that a catalyst, you understand, is really not a reactant and is not considered a product. And in most cases, a catalyst actually doesn't even get used up during the reaction. It's still there when it's all said and done. A lot of times the way catalysts work is they provide like a nice location for everybody to come to. So everybody's sort of attracted to the catalyst. All the reactants sort of end up at the same location. And what that's going to do is basically allow them to start reacting a lot faster than if they had to kind of float around and find each other, or if their gases flying around to find each other. So a lot of times catalysts are metals and sort of substances that allow everybody to sort of congregate in the same location. And the end result is it can kind of speed up a chemical reaction. We'll get back to that later. So as I mentioned a little bit earlier there, again, our abbreviations, this actually should be a capital O. It should be carbon monoxide there. So as we see there, carbon monoxide, some oxygen, and CO2 are all gases. Obviously, we could have things that are solid, liquid, and gas along the way. And like I said before, a lot of times we will also sometimes use equations to represent physical sort of processes. It's important when you write chemical equations to also remember that there are certain things that have sort of special formulas. And this is a case, for example, if you're given something in words and they say, hey, you reacted hydrogen gas or molecular hydrogen or molecular oxygen. A lot of times people will sort of mess up on things like that and just write like H for hydrogen. But we know, as we talked about before, right, hydrogen by itself actually comes as a diatomic molecule. Our oxygen also comes as a diatomic if it's just the element really by itself. And that's really important in terms of the balancing part of the equation. A lot of times people will just write O or H and things like that, and they'll never be able to balance the equation. Obviously, they'll have the wrong equation. So as we'll talk about in a couple of minutes here as well, it's really important to make sure that you do start with the actual correct formulas before you get into any of the balancing part, because you really don't start with the correct formulas like we did sort of with nomenclature, you will have a difficult time. Also, sometimes water is just written on top of the arrow, and that usually implies some process of you're dissolving something in water, again, getting you that sort of aqueous solution. So let's talk about sort of balancing equations and some approaches to take. So first off, if you happen to be given everything in words, like I mentioned earlier, you definitely want to make sure that you start with those correct formulas. Very common people screw up because they try to balance and write the formulas at the same time. And it's very common in a process where maybe you're given the front part of the equation and you need to kind of come up with sort of what's on the other side and then balance the equation. And it's very common that people will write the wrong equations because they're trying to balance it as they are doing it. And the proper order is to make sure you get the right sort of formulas down first, then go back and balance. So just keep that in mind as you go through it. Once you get all the correct sort of formulas down, you should have the unbalanced equation. Then the most important thing is to start balancing it. So what we do when we balance equation is, frankly, the only thing that we change are the coefficients. So when you balance the equation, it could only be the numbers that come in front of the formulas are what you change. So if you had water, you would put a number in front if you were looking to balance it. You never change the smaller numbers because frankly, you just change what it is. And you never do any weird things like people like to do, like put big numbers in between things and stuff like that. Don't do any of those crazy things. So when balancing the equation, we should only put numbers in front of those coefficients. The goal is obviously to balance. Most people do sort of a trial and error, put a number on this side, put a number on that side of the arrow, and hopefully at some point everything balances out when it's all said and done. The goal obviously is to balance it out so that whatever amount of elements we started with, say we started with 6 carbons on the left, we should end up with 6 carbons on the right. They may be in different compounds and stuff on the right hand side, but we should not lose anything. And that's the idea of conservation of mass and all that. When we are dealing with chemical reactions, as I mentioned earlier, it is just electrons, which means no elements change, right? Because the only way we could change an element is to change what thing? What particle really determines the element? It's a proton. So because in chemical reactions, it's just electrons involved, no protons get changed or anything like that. There is that conservation of elements as it goes from kind of left to right on the equation. And the only place ever that happens is really in nuclear reactions. We don't get that conservation, but in chemical reactions, we definitely do. So really the goal is to keep balancing it. And there's really kind of 2 things you want to make sure of when it's all said and done. First off, obviously you have the same number of elements on each side. Secondly, you have all whole numbers when you're all done for your coefficients. And not only all whole numbers, but they do need to be the simplest set of whole numbers. So this sometimes occurs because people can sometimes see maybe larger numbers than other people to balance it. So for example, let's just say we had 6a plus 4b gives me 2c, and we'll just say that was a balanced equation. When we look at all these coefficients, although it is technically balanced, we technically go through, right, and basically divide everybody by 2 and reduce it down. And you should do that, and you would get 3a plus 2b gives us c in this case. And this would be the properly balanced equation. So, and again, it sometimes happens because people can see larger numbers, which is perfectly fine. You just want to double check that when you're all said and done, if you can go through and reduce all the coefficients down and still end up with whole numbers, then you should definitely do that. That's the proper way of balancing an equation. Any questions on that there? All right, so let's take a look at one here together. So personally, when I look at an equation like this, there's a couple things I personally like to do. And I think it's a good approach, and you might want to do it yourself. So, it's very helpful sometimes to frankly make a table and see what you got going on. So you got the reactant side, you got the product side. We have 3 elements involved here: nitrogen, oxygen, and hydrogen. Left-hand side of the arrow, we got 1 nitrogen. Right-hand side, we have 2 nitrogens from there. Left-hand side, we got 1 oxygen. Right-hand side, we got 1 oxygen. Left-hand side, we have 2 hydrogens, and right-hand side, we have 2 hydrogens. So the nice thing about a table is if you're not really sure where you should begin, it oftentimes can point you in a very good direction. We could clearly see here from our table that hydrogen and oxygen at this point, it's all good. So nitrogen seems like a pretty logical place to begin. We're going to balance it, remembering to put only coefficients. So we could fix nitrogen's problem on the left by simply putting a coefficient of 2 in front of it. When we do that on the left-hand side, we got 2 nitrogens. As we multiply it in, and by the way, the 2 goes for the nitrogen, and it also goes for the guy behind it as well. The oxygen then would also be 2, and hydrogen here would be 2. As with the case with sort of balancing equations, as soon as you fix one thing, you kind of usually screw up everybody else. So in this case, we fixed the nitrogen, but really screwed up the oxygen. So that is sort of an easy fix at this point. We could go to the right-hand side, and we can simply put a 2 in front of the oxygen. Again, the 2 here will go to the hydrogen and the oxygen here. So in the case on the right-hand side, we have 2 nitrogens. We have 2 times 1, which is 2 oxygens. And now hydrogen, we have 2 times 2, which is 4. So now we're getting closer. We got our nitrogen balance. We got our oxygen balance. At this point, we are left with hydrogen, which can simply be found by going back to the other side and throwing a 2 there. That gives us 2 nitrogens, 2 oxygens, and 2 times 2 is 4 hydrogens in this case. Any questions on that there? So that's a really good way. Make a little table, kind of go back and forth as we did. And really at some point, everything should sort of fall into place. If you find yourself going back and forth and you're full with numbers on the front and you're still not balanced, something is probably wrong. And probably what's wrong is you have an incorrect formula, probably in a lot of cases that's written there. Any questions on that? Yes.
For like questions for say a quiz or a test, will we be given parts of both sides, or will we have to figure out like what the product would be?
I would say at some point by the end of this chapter, maybe, yeah. So we'll talk about how you can predict what will go on the other side. I would say probably a majority of what you would probably be given would be the entire equation. You might have to balance it. But there definitely could be some questions on certain types of reactions where you could be able to predict what goes on the other side. A lot of times in labs, they have a very common like give you stuff where you have to kind of predict what's on the other side and stuff like that. But we will talk about different types of reactions later on this chapter. And at some point, you might be able to predict some of those. Other questions? But probably a vast majority, you would be given an equation where you had to balance it, I would think. All right, so why don't you give this one a go here, see what you come up with. Okay, let's take a look at this. So same approach here. I'm just gonna make a little table here, see where I'm at. Left-hand side, I got 3 carbons. Right-hand side, I got 1. Left-hand side, I got 8 hydrogens. Right-hand side, I got 2. Left-hand side, I got 2 oxygens. And right-hand side, I have 2 oxygens there, plus 1 more there. Gives me 3 total oxygens at this point. So again, in this case, if we look at it, probably the easiest thing to fix right off the bat is carbon, right? So we could very simply fix carbon by putting a 3 in front of it. When we do that, again, the 3 goes for everybody that is here. So that gives us 3 carbons. We still have 2 hydrogens. And in terms of oxygen at this point, we have 6 oxygen there, plus again, 1 more over here, which gets us to 7 at this point. The next easiest thing probably to fix at this point would be the hydrogen, as it's in just one thing by itself. Oxygen's in a couple of things there on the right. We can simply fix the oxygen by also going to the right-hand side here and actually putting a 4 in front of it. Again, that goes for both guys that are there. So that would give us 3 carbons. 4 times 2 is 8 hydrogens. Now in terms of oxygen, we still got 6 there, but now we got 4 more over here. And that gives us 10 total oxygens on the right-hand side. And that's good because now we can simply now go back to the left-hand side there. And that's going to be a 5-pack right there. That's going to be 3, 8, and obviously 5 times 2 is 10 in this case. And now we would have obviously our balanced equation. Any questions on that there? Okay, so since we're getting in, we will lay it up there.